the coupling. And the reagent that's used there is this guy here. It's called dicyclohexyl carbodiimide. We've seen guys like this before. It's a bisimine analog of carbon dioxide. Okay? So that carbon is quite reactive. It's quite electrophilic. Okay? And the cyclohexyl groups are put in there to make it soluble, and more importantly, this thing acts as a dehydrating agent. So it picks up water like a shot. And you can see why. This is very hot carbon. Water will attack here, and OH will eventually wind up here, and proton will wind up here. It's like an imine hydrolysis. Okay? And when you go through with this, you actually get this guy here. That's the water adduct after you shift the protons around, such that, actually we're going to do this in a minute. Because initially what you get is an enol, an imine enol with a hydroxy here, and that tautomerizes to the amide on this side. So this is a so-called urea derivative. Urea, the parent urea, was talked about, I think, on page 3 of the textbook, if you ever read page 3. It's the stuff we excrete in our urine. That's one of our primary ways of getting rid of the nitrogen that we ingest in our food. This one is dicyclohexyl, and the reason dicyclohexyl is used here is, in part, as I said, because of solubility issues, but the product is totally insoluble when it's formed, and it precipitates out. And that's very, very useful to, of course, remove it from your reaction mixture. You don't need column chromatography or fractional crystallization, tricks like that. And that kind of simple removal, of course, is superb for automation, because in automation, you just shove this stuff through a filter, and it filters off this guy here. So this is nothing else but a dehydrating agent, and notice that the reaction of a carboxylic acid with an amine to make an amide is a dehydration. Okay? Water is the other product. Okay? So how does this work? And notice we are avoiding here now making an acid chloride, our classical way perhaps of having pulled off this transformation. In the classical way, we would have had these two separate. First make the acid chloride, then add the amine. You can't have all of these in a pot. Here we're actually mixing all of these three reagents in the same pot, and off it goes. So here's the mechanism, which looks a little busy, but in fact it's quite simple. I won't test for that though, so I just want you to follow what is happening. So here we have alanine protected with a tertiary butoxycarbonyl at the amino end. And what we want to do is react this carboxy end with the amino end of glycine. So we want to make alagly. So it's protected correctly at the amino end, and we have in the same pot, as we'll see in the next slide, also the carboxy end protected glycine. So it's ready to react to make an amide. But it can't yet because this OH is not, or this carboxylic acid doesn't have a hot enough carbonyl group to enter into additional elimination. So it reacts first with this dicyclohexyl carbodiimide in a step that activates this group. Okay? And how does it do it? It just adds. Okay? So in fact, the first step is protonation on nitrogen, the typical imine protonation, and then carboxylate anion that you get attacks here. Okay? So we get carboxy here, proton here. And here it is. Okay? Here's the carboxy having attack here, and here's the proton. Okay? And the other side, the amine is still intact. Now, when you stare at this, you realize what you've done. If you turn OH into O, this big blob, which is an O big blob, that's actually an excellent leaving group. Because when you realize that when you think this through and make this guy leave, it puts a negative charge on this oxygen, and that's an excellent negative charge to be stabilized by these two inductively electron withdrawing nitrogens, but also by resonance with the CN double bond. So what have you done? You've done exactly the same thing that we do when we treat a carboxylic acid with thionyl chloride to make it an acid chloride. OH, bad leaving group, is turned into Cl, good leaving group. Here, OH, bad leaving group, is turned into O blob, good leaving group. And so here's it's repeated, but now with a color scheme, this carbonyl is now activated. It's got an excellent leaving group. And so now we have the carboxy end protected glycine, simply protected as a metal ester. And it just does additional elimination in the usual fashion. And it kicks out the leaving group. And remember, when you kick out the leaving group, you get O- here, which then is really an enolate type O-. And so in the end, it gets protonated on nitrogen because this is the more stable tautomer where you have the CO double bond as opposed to the CN double bond. So all the principles that we've learned in the past 3 months come to play here, particularly in the past month and a half. And here's the new bond, okay? And so here's your dipeptide, which is still protected at the amino end, of course, as a tertiary butoxycarbonyl, and at the carboxy end as a metal ester. Okay? And so this beast here is abbreviated like this, T-Boc alagly O-methyl, to indicate that's a metal ester on the right. That's a T-Boc tertiary butoxycarbonyl protecting group of the amine. I won't test for any of that, although I will write sometimes these things and names under the structures, but you get all the structures, so you don't have to worry about that. And then the last step to liberate the dipeptide is to just hydrolyze this off. In this case, you can just beat this with acidic water, because the acid will take this off as tertiary butylcation, which goes off, CO2 will blow out, the amine is free, and the acid water will just hydrolyze the metal ester like any metal ester. So that's the trick, and that's all there is to what you should take home with you for next week. Sorry, 2 weeks from now in the final exam. And so the last bit I wanted to talk to you about is totally general education to give you a glimpse on how DNA and RNA are involved in preserving and life over generations, and what the structural basis of this is. So DNA and RNA are related to each other structurally. Okay? But DNA is a polymer that is made out of sugar molecules linked with phosphates, so phosphoric acid comes in. So that gives a backbone. And at the anomeric carbon, the hemiacetal carbon of the sugar, are sitting bases. Bases meaning nitrogen heterocycles, which turn out to be all aromatic nitrogen heterocycles of the type we discussed a week or two ago. And it's the sequence of these bases that is a language almost. You can view it in terms of the written word as letters. Okay? And in DNA, in our DNA at least, there are 3.2 billion of those. And so it generates a whole book. And you can, if you want to choose our body as an analogy to a car, it's like having the manual on how to build a car and maintain a car, which presumably would be, I don't know, 500 pages, let's say. Okay? And so the total information is in there, and it's something that if you want to keep on building this car, has to be preserved. Okay? Absolutely. No tinkering with it. Okay? So DNA itself can't get involved into any active chemistry, so to speak. But to help read off that information, we have RNA. Okay? So the difference between the two is just in the sugar. So DNA uses deoxyribose, whereas RNA uses ribose. Ribose was one of our pentoses, okay, 5 carbons. So it's not in the family of glucose and fructose. It's family 1 up in the family of aldoses that we saw a few weeks ago. And it's shown here in the cyclic hemiacetal form, which, of course, is the prevalent form of that sugar, because it prefers to be in the cyclic form, very little of the open form. But remember, this is a carbon here that's labile, okay? But it sits there, and you make a polymer of that in RNA. DNA uses a derivative, and we'll see in a second why, for self-preservation, actually, as it turns out, where it has evolved to take away that OH group, okay? Which that second OH group next to this one, as we'll see in a minute, is actually causes self-destruction, the decomposition of the polymer. So cleverly, this is, of course, by trial and error, eventually was the one that succeeded. Okay, so what sort of structures are we talking about? Here's the polymer. Okay, it's a polymer backbone where the sugar uses 2 of its hydroxy functions, namely the dangling hydroxymethyl and the hydroxy at carbon 3, to link to phosphoric acid. Okay? So it's these 2 OHs and these 2 OHs that make esters with each other, and they do this in this repeating sequence. And that gives you the backbone of the structure. Notice in DNA, there's no OH here, so there was no option anyway. There's a third OH that could have been used, but you already know why nature didn't use that. That's a disaster, because that's a hemiacetal OH. Okay? It's a labile unit. Okay? And this carbon, this ring can ring open, but more importantly, this OH is readily displaced in synthetic transformation. So it's a reactive unit. Okay? So nature preferred to not touch that for the polymer backbone. Okay? And then notice, nature did use the lability of this OH function to introduce the third and perhaps most important piece of the polymer, namely the bases. And so it's a nitrogen base, so it actually replaces oxygen with nitrogen. And that, we haven't done that reaction, but you can imagine it's easily done with a mild acid and an amine. You protonate here, water takes off, you get a stabilized carbocation here, you trap it with a nitrogen. Okay? So that's how one would do it in a test tube in the lab. Nature does it with the help of enzymes. And so here's the base scenario in a sequence, and it's the sequence that are the letters of the alphabet. And so depending on how these letters are arranged, they make words and sentences and entire chapters. And there is the information embedded in those. It's the structural information of our manual on how to build a car, or in this case, how, as we shall see, how to make peptides, which are the ones, the moving pieces in our body, just like the moving pieces in your car. And interestingly enough, nature was happy with just 4 bases. So there are 4 different bases in DNA, and also 4 bases in RNA. And so what are these bases? They're all aromatic heterocycles. And for RNA, it's cytosine, adenine, guanine, and this guy, uracil. For DNA, it's this guy, cytosine, thymine, adenine, and guanine. So for DNA, it uses thymine instead of uracil. Now, first of all, let's look at the structures. These are all aromatic, not immediately obvious. The way you can visualize this is by recognizing, and now here I picked cytosine, by recognizing that there's a very strong contribution of the dipolar resonance form to these amide structures, pulling the double bond in here, okay? And then you can see this is basically a pyridine. Okay? Well, it's an aza pyridine. So 2 nitrogen, 2 pyridine-like nitrogens. Point being, it's 6 electrons in the cyclic array. Okay? This one here is easily recognized. That's like an indole derivative, where 3 of the carbons of indole are now replaced by pyridine-type nitrogens. Okay? You count the electrons, it's 10 electrons. 4 and plus 2, Huckel's rule, aromatic. Okay? So now the interesting question that you may ask is, why did nature switch from uracil in RNA to thymine in DNA? And the reason is the following. This guy, cytosine, every now and then, and that's present in both RNA and in DNA, under certain conditions, can hydrolyze what amounts to an enamine type, an aza-enamine function. If you play this through, add water to this, and kick out ammonia, this will actually turn into uracil. Okay? Now, for DNA, any change of the base is a disaster, because you're altering the manual, the base manual that has to be absolutely rock stable in order for cells to reproduce and so forth. It has to be always the same imprint. If you're changing one of the bases, that causes a mismatch, a misreading, and called a mutation, and all hell breaks loose, typically cell death, but in nasty cases, you get cancer or some adverse medical condition. So when this happens, and DNA has this guy that can turn into that, when this happens, fortunately, in order to protect itself, evolution has generated a police system, a repair system, that watches out whenever this guy actually hydrolyzes to that, and it's a repair mechanism that gets rid of this guy, okay, when it's formed. So that it happens rarely, but there's a protection mechanism set up with an enzyme or a protein that comes in and mops this up and removes the uracil from the place where it might have played the role of cytosine, meaning a mutation. Now, this repair mechanism would not be possible if this base had been uracil, right? Because then, if uracil is already part of DNA, you can't develop a mechanism like that. And so instead, nature just changed the structure of this to introduce a methyl group, and that is much more stable, and that's the story why this is there rather than that. Now, for RNA, which also contains cytosine, the hydrolysis of cytosine into uracil causes its destruction. But RNA is not important. RNA is a workhorse. Okay? So it's like, in RNA is actually the nucleic acid that makes a copy of a certain piece of DNA and then takes it out and generates specific polypeptides out of it. So it's like you're driving your car, your left front light goes out, you need to replace the bulb. What do? You go to the manual. That's your DNA. You go to page 149, and if you're lazy, you copy it with a copying machine. That's what RNA does. It takes one page, copies it, okay? And then it takes that, and with the car, you fix with the one page, you fix your light. RNA makes a particular polypeptide. And so if your copying machine breaks down or the toner goes out or something, no big deal. You just fix the add toner or fix the machine, and you make your copy. Okay, so in a similar sense, RNA is disposable. Whereas if your page 149 in your manual is missing, or it's been garbled, you're screwed. You can't do your life, right? So that's what is going on here. Extreme protection of DNA. And the other guys are just helping out. So here it is again, and another little tidbit that I alluded to earlier, which I also find rather interesting in terms of evolution. The reason that DNA uses the deoxyribose, no OH here, is because with an OH here, that OH can swing around and do an intramolecular transesterification. You remember transesterification? It's a transesterification on a phosphate, but it's the same mechanism. It's addition elimination. OH here comes in here, adds, this electron pair goes out, comes back in, and the leaving group is this guy now, meaning you're breaking the chain, you're killing your polymer, and that's death, right? DNA information is lost. And so nature evolved such that this OH is gone. For RNA, where this OH is there, it doesn't matter. Again, RNA, in a way, you can call it disposable. You can always make new RNA, and if that one screws up, it just doesn't make in this particular round that particular polypeptide from that particular RNA, but there are millions of other RNA copies, so no problem with that. So these strands, which can be extremely long, with molecular weights that go up to about 150 billion or so. Remember, it's 3.2 billion base pairs. In your book, the number is still 2.9 billion. There's now an updated number of 3.2. So 3.2 billion of these guys. So these are enormously long chains. You can see them with the eye. They're visible to the eye. And the cute thing about them is that they're arranged in a helix, and they link up with a second DNA strand. So two strands get together and start winding around each other, as in this famous picture of DNA. And the way they connect is by hydrogen bonding. So this is a very similar principle to what we just saw in secondary structure of polypeptides. There is a propensity of these guys to get together and be held together by hydrogen bonding. And in the DNA, it also generates the helix. And so the question is, what is holding these guys together? Hydrogen bonding of what? And that was one of the greatest detective stories of the mid-20th century. Nobel Prize was given to these guys, Watson and Crick. They exploited the finding that there were always, in DNA, there were always as many adenine, called A, molecules or bases as there were thymine, and guanine, as many guanines as there were cytosines. In other words, there was a one-to-one relationship with those. And eventually, by a lot of tinkering and building models, they figured out that these pairs, AT and GC, are perfectly or particularly good in forming hydrogen-bonded dimers. And there's the hydrogen bonding that occurs. And if you make an electrostatic potential map, you actually see this very nicely. Blue is electron deficient, red is electron rich, right? So blue is in front of red is in front of blue. And the measured binding energy is 4.3 kcals. And for GC, there are three of them, guanine, cytosin. Again, you can see this nicely in this potential map, electrostatic potential map. And the binding energy is even more because now there are three of them. And again, remember, small numbers, but you multiply this by 3.2 billion, and you get an enormous number, a very, very strong aggregate, which of course involves all of the bonds together. And the beauty is that if you can still, because the individual bonds are relatively weak, unravel them one at a time. And that's the essence of the reproduction. And so here's so this gives rise to this double helical arrangement where one strand of the DNA has a certain sequence, and it faces an opposite strand by doing hydrogen bonding to always the complementary base that's on the other side. So if we have C in the red strand, it will then make a hydrogen bond to G in the green strand. And A will always be opposed to T, and T to A, and so forth. So you have two strands that have complementary type of relationship of these base pairs. I will call them image and mirror image, although it's not in that sense image, mirror image. But let me use that language because it sort of describes what's going on, where if you describe one set of bases, AC as the image, then their mirror image will be T and G. And so there's the complementarity. A is always in front of T, G always in front of C. Okay? So GC, CG, TA, AT, da, da, da. Okay. So the replication then occurs by slow unwinding at the end of the old DNA strand, making an open strip of uncoupled DNA strands, the red or brown red versus green, and through the machinery of DNA synthesis, lots of riboses and phosphoric acid and the bases around, you construct a new DNA helix as the mirror image of the existing helix. So we call this guy the image. Then a new DNA is being built by always stitching together complementary bases, complementary to the bases already here. So this is the mirror image, this would be the mirror image. So if this is the image of the old DNA, then of course this is the mirror image of the old DNA. And that one does the same thing, except that the mirror image of the old DNA generates now its mirror image, which is actually the image of the old DNA. I think the color coding actually shows what's going on. Okay? So that's brilliant. Okay? By playing this game of complementarity of the bases, you can do this coupling. And so when you reproduce this, the error rate is just unbelievably small. It's 1 in 10 billion, in part for 3.2 billion base pairs, in part because whenever there's an error, there's already an army of enzymes and proteins and other molecules sitting there to fix it. Okay? Because absolutely no error is allowed in order